the two other questions that you had then, you had an iron, no, actually, I'll do the one there firstly, you know, where you had the ammonium iron 2 sulfate. I'll just run through that question first. So it asks you to explain a standard solution. So a standard solution is a solution of precisely known concentration, and two essential properties of a standard solution: pure, stable, soluble, solid. Remember, we had 3 S's and the pure. Now, why was it necessary to use... Now, we've gone through these answers already in the previous video. So why do you add some sulfuric acid when you're preparing the ammonium iron 2 sulfate? The reason for that, of course, is to prevent oxidation of Fe+2 to Fe+3 by what? By oxygen in the air or by oxygen in the water. And part 2 of B then says, why do you add more sulfuric acid when you're performing the titration into the conical flask? Well, again, the reason for that is to supply H+ ions to fully reduce the MnO4 minus down to Mn+2. Or to fully reduce, you could just say, instead of saying MnO4 minus like I did there, you could just say the Mn+7, because that is the oxidation state of the Mn there, to Mn+2. Okay? Now, part C, I want to go through this in a bit of detail because I kind of missed that, I think, in the video that I did. Describe fully the procedure used. Oh, no, not this one. The procedures used during. Now, they have during the titration in italics there. Now, lads, there was 12 marks going for this, so you needed to make 4 points. So if you're asked anything about during a titration, you're going to say that you're continuously swirling the conical flask so that the reagents are mixing. You could say that you rinse down, stop the titration and rinse down the sides of the flask with deionized water. Again, just in case there's any solution high up on the neck of the conical flask, it hasn't come in contact with the solution in the conical flask. So you need to make sure that every drop from the burette has actually reacted with what's in the conical flask, because it's been taken into account in the volume from the burette, so it needs to be mixed, or it needs to react with the solution in the flask. So rinsing down with deionized water. You perform a titration using a white tile, so the conical flask is on a white tile, it's easier to see the colour change that way. You carry out a rough titration, and then you perform 2 accurate titrations that are within 0.1 of each other. Okay? Now, what observation indicates the correct endpoint has been reached? Now, lads, do you remember we put the purple permanganate into the burette, and in here you put in your 25 cubic centimetres of your ammonium iron 2 sulfate, and you also added some sulfuric acid, and we've gone through the reasons for that. So this is your iron solution in here. Now, you've Fe+2 ions in there. Now, as you add Mn+7, those Mn+7 ions get reduced to Mn+2. The Fe+2 ions get oxidized to Fe+3. Okay? But what about when your endpoint is near and all of these Fe+2 ions have already been oxidized to Fe+3? So there are no more Fe+2 ions in here. Now, if you don't have a species that's going to be oxidized, you cannot have reduction, because you have to have something losing electrons for something to gain electrons. Okay? So if all of the Fe+2 ions have already been oxidized to Fe+3, then you cannot have any further reduction, of Mn+7. So what happens then, okay, is you have 1 drop of Mn+7 here that is not reduced. So you've got a purple drop in a whole flask of solution, so it looks pink. So what they're looking for you to say is that there is a permanent pink colour, or that the pink colour remains, something like that. So the observation at the end point, permanent pink colour remains. It does not go colourless. Permanent pink remains. That's all you'd actually have to say there, because there's only 3 marks going for it. But I just wanted to run through the explanation of that there. Now, part D then, you have to calculate the number of moles. Now, lads, with this one, you were using your primary standard, your ammonium iron 2 sulfate, and they told you that you'd 8.82 grams of the ammonium iron 2 sulfate in 250 cubic centimetres of water. So the first thing you're going to have to do there is you're going to have to calculate the molarity of the ammonium iron 2 sulfate. So multiply by 4 to bring it to grams per litre, so that's grams per litre, and then you divide by, what is it again, 392, isn't it? So that's the MR, 392 is the MR of ammonium iron 2 sulfate. Now don't forget to add the water, the whole lot, and that gives you 0.09 moles per litre. So like, do you remember when you were given the MR, it's all of it, do you remember? SO4, FeSO4 and 6H2O, so the whole lot adds up to give you 392. And remember, you must show the working out of the MR as well when you're doing that. Excuse me. So this is the molarity of our ammonium iron solution. Okay, so that's what we know the concentration of. So we know the concentration of the ammonium iron 2 sulfate. We know that we used 25 cubic centimeters of that in the conical flask. They pipetted in. So we can calculate step 1, stick with the steps, lads. Step 1, number of moles of the solution we know the concentration of. So V by M all over 1,000. 25 times 0.9 divided by 1,000. And when you do that, you get 2.25 by 10 to the minus 3 moles of iron in that 25 cubic centimeters that you put in to the conical flask, okay? Then they asked you to calculate the number of moles of permanganate that will be required. Ratio, number of moles of the solution that you know the concentration of, and then ratio. Now, from the balanced equation, the ratio of permanganate to iron is 1:5. These are moles of iron that I have here. So I need to divide by 5 to get the moles of permanganate. So when I do that, then you're getting 4.5 by 10 to the minus 4 moles of the KMnO4. Okay, that's what you need to react with all of the iron that's put into that conical flask at the start. Then your step 3 is equating moles to volume. Now, what volume of permanganate did it say? They gave you the average titration and their volume in the question, 20.45. So now you need to calculate moles in a litre, not in 20.45. So divide by 20.45 to bring it to 1 cubic centimetre and then multiply by 1,000. So 4.5 by 10 to the minus 4 moles was present in 20.45 cubic centimetres. So like I said, divide by 20.45 to bring it to 1 cubic centimetre and then multiply by 1,000. And you're getting the molarity of the permanganate then at 0.022 moles per litre. Okay, so that was the end of that question there. All right, now you have now standardized the KMnO4. You now know the concentration of the KMnO4 because you performed a titration to calculate it. You then would have used this standardized KMnO4 and titrated it against an iron tablet solution to calculate the concentration of the iron tablet solution. That's how this works, okay? Now, the iron tablet question that you had then, the theory there was, why was it important again to use sulfuric acid when you're making up the solution? Again, same answer, to prevent oxidation of Fe+2 to Fe+3 by oxygen in the air or by oxygen in the water. Describe the procedure. That's well done in your revision book there. You'll say crushing the tablets with a mortar and pestle. Wash the tablets off into a beaker containing deionized water and some sulfuric acid. Stir to dissolve and all of that, those procedures, okay? Why was more dilute sulfuric acid added before the titration commenced? To supply H+ ions so that the MnO4- or the Mn+7 is fully reduced. That's your answer there. And how was the endpoint detected? Well, again, permanent pink colour. Okay, now your calculation now next. So it said that, look, it's telling you straight away. So search for the information, okay? It's telling you straight away that this is the molarity of the KMnO4. So the first thing I'm going to do is I'm going to get the number of moles of the solution I know the concentration of, which is in this instance KMnO4. So 13.9 times that all over 1,000. So the concentration of MnO4 this time works out so to be 1.39 by 10 to the minus 4. And will you please write down what the solution is that you've just got the number of moles of? So that's the number of moles of KMnO4. Remember now that the KMnO4 was in the burette. So that's the number of moles that went down into the conical flask. Now, how are you going to know how many moles of iron would have been needed to react with that much KMnO4? You use your ratio. Manganate to iron is 1:5. You know the moles of permanganate, okay? So multiply by 5 to get the moles of iron. When you do that, this is your moles of iron that would be needed to react with all of the permanganate that went into the conical flask, okay? Now that you have number of moles, our third step is you equating moles to volume. What volume of iron tablet solution was put into that flask? 25 cubic centimetres. So now you can get moles per litre of the iron solution. You can either multiply by 40 to bring it up to 1,000, or alternatively divide by 25 to bring it to 1 cubic centimetre and then multiply by 1,000 to bring it to moles per litre. When you do that, you're getting the concentration of the iron solution out at 278 moles per litre, or 278 molar. That's a 2 there. Okay, so that's part 1 then. That's your answer to part 1. How would you now calculate the mass of iron in 1 tablet, right? Now that's mass per litre. Now what they did was they put 4 tablets, okay, so we need the information now. They put 4 tablets into 250 cubic centimetres, okay? So we now need to know the mass of the iron in 1 tablet. That's moles per litre, okay? So if I could figure out moles, how many moles of iron was in that 250 cubic centimetre flask by dividing by 4. So you're going to get 6.95 by 10 to the minus 3 moles of iron in 250 cubic centimetres, okay? Now there's different ways of doing this. The order doesn't really matter, okay? Now I can go for mass of iron. How will I convert moles of iron to mass of iron? Now remember lads, it's just iron, it's just Fe, so you multiply by 56. So mass of iron then, right, 0.3892 grams of iron in the 250 cubic centimetre solution, okay? So that was 4 tablets. 250 cubic centimetres was 4 tablets. So now I need to divide that value by 4. And when I divide that value by 4, then sorry, I'm getting 0.973 grams of iron in 1 tablet, because I divided the 250 value by 4, okay? And that's my answer to part 2. And then finally for part 3, they're asking you the percentage mass of iron. So you put the amount of iron, which is what we've just gotten there in part 2, all over the mass of 1 whole tablet. Now, I told you in the question, the mass of 1 whole tablet was 0.36. Sometimes you'll need to divide, they might give you the mass of the 4 whole tablets, and you might have to divide the value by 4. But there in that question, they told you each of mass. So each tablet had a mass of 0.36. So when you work that out then, you're getting the percentage iron in each tablet at 27%. Okay, thank you.